Okay, so here we go. This is the week 04. This is last week's distance learning, the FRQ practice problems. I know a lot of you didn't show up for that live session, so I still wanted to make sure I posted it so you'd have access to it because these were some good questions, and I can explain a couple little details on it. I'm not going to read over the whole thing, but hopefully you kind of understood it. But the spring on the box at first hit the spring. Indicate whether the work done by the spring would be positive, negative, or zero. Well, you want to start with your justify, and what you have to start thinking about is what does a spring, in a sense, do? And a spring is like an energy suck, right? It's a potential energy thing. So the spring is going to slow down the speed. So the box, which has positive kinetic energy, has the spring removes or sucks, and you don't want to use the word sucks, but I've used it in class, the energy out of the system in order to slow it. The spring stores energy, so it's by its nature, if you store something, you are removing something because you're removing it from somewhere else to store it somewhere. Now, although in your house that might be a positive thing, you're removing it from something, so you're creating a vacuum, which is a negative, so to speak. How that kind of works. So we're moving something, which in physics is negative. Also, you could say that the force the spring pushes on the block is opposite direction of the motion of the block, and usually we're gonna say positives in the direction of the motion, which is work equals FD. So that means it's still going to be negative work. So it has to be negative. So the answer is negative. And again, you want to really start with that rationale first. All right, calculate the magnitude of the work described in part I. So work equals F dot D, and F dot D means FD cosine theta because they have to be parallel. So F equals MA, we know that. Acceleration is going to be this. This is a variant of equation number 5. Now your initial velocity is going to be, you don't know, or do you? Oh yeah, you give it to you. But what's your final velocity is going to be 0 because it's going to stop it. And that distance it's going to press it is going to be 0.05. Now we're saying negative 4 meters per second, and then it's squared because that number has to be squared. We're saying it's negative y. Well, v naught equals vi. It's a v naught square. Vf squared equals vi squared plus 2a delta x is the equation. And so to get that v naught away from the a, you have to subtract it. So you end up getting negative 16 meters per second squared. Half of 2 is 1, and 4 squared is 16, and that's negative comes afterwards. So work equals 20 times 16. Well, where'd the 20 come from? Well, it's the mass it's giving you. It's the second, well, basically the second thing it tells you, A. Well, that's the first thing, A, and then the second, you get the idea. Times 0.5, that's our distance. So this is our force. So this is MA, that's our force, and this 0.5, that's our distance. We plug those in, and there's another way you could have solved this, which is work equals change in kinetic energy. Now, you have final minus initial. Well, your final kinetic energy is 0, so you're able to have a negative initial kinetic energy. So it works out there as well, which kind of goes with this. Equals 1/2, 20 kilograms, 4 meters per second squared. But you know that answer is going to be negative. Wait, Ms. Cooper, why is it positive here and negative here? Remember, it's negative here because of the equation. So it was Vf squared equals Vi squared, or V squared equals V naught squared plus 2a delta x. Well, if you're trying to solve for a, you have to subtract over that V initial or V naught part. So that's what made that negative. This is negative simply because it's final minus initial, and this is our initial right here because there is no final. And you still get 160 joules. Negative 160 joules. All right, moving on. Okay, so B, calculate the spring constant of the spring. So K initial equals, final potential. So 1/2 equals 1/2 kx squared, right? So it's all spring. Yep. So what's going to happen here is you got 160 joules. We already know that. Now you could have said well, can't I just cancel out the 1/2? You could have, but you already know the 1/2 mv squared is 160 joules. That's from before. That's your initial kinetic energy. So equals the 1/2 kx squared. So K then is going to equal, we can do some algebra here, 2 times 160 over x squared equals 1,280 Newton meters. And that is our spring constant. Okay, I should ask you to find. C, calculate the magnitude of the maximum acceleration on the box. So the maximum acceleration, so A equals F over M. Okay, so F is kx. That's hopefully something you remember. K times x over M, right? So you're going to have 1280, which we just found, times 0.5 divided by our m, which is there, and 32 meters per second squared. which is kind of neat because 32 feet per second squared happens to be the acceleration due to gravity on Earth in the imperial system. Worthless fact if you're curious. Now, we did have some cool questions, but I can't remember what they were, so next time show up to the live session because I don't always remember to record them because they end up being an hour when this video might only be like 15 minutes. Calculate the frequency of the oscillation of the box. Okay, so the frequency of the oscillation, let's start with that one. So frequency is 1 over period. Hopefully you remember that. And period was 2 pi m over k. If you can't remember that, 2 pi m over k. So 1 over 2 pi k over m is going to be our inverse of it, basically. So 1 over 2 pi, we got our k from up there, which is 1280. And then we have our m, which is right there. We plug those in, 1.27 hertz. Easy peasy melon squeezy. Moving on. All right, now, I did mention that you will not have to draw graphs, but that does not mean you won't have to describe graphs. And that's an important thing to understand. So even on your test today, or this week, which is actually in It's Learning, you have to describe either a free body diagram or a graph. So you're not going to have to draw them, but you will have to describe them. So we're going to talk about this one. And I do have these points of limits. That's kind of where we're going to from there to there. And it wants the kinetic energy of the oscillating box as a function of position versus x. Well, think about this for a second. The kinetic energy is when the speed is going to be the greatest. Well, where is the speed going to be the greatest? At 0, when it's not pushing it in or out. When it's being all the way compressed in, because it's oscillating, remember, it's got no speed, so it's going to have no kinetic energy. When it's all the way out, it's being stopped, so it's got no energy. Now, how would you describe this? I might describe this as a frowny face, or a half circle, or a half circle that is, I'd tell you, a frowny face half circle. I don't know, you could say concave or is this concave or this this is concave. So a concave half circle, frowny face from negative 0.5 to 0.5 with the maximum value being at k. And they might actually ask you for that maximum value. You should have to figure that out if you needed to. 1/2 kx squared, if you will. All right, questions on that one? Okay. The next one was interesting. It was the acceleration. So again, we're going to have our limits here. So what is happening to our acceleration? Well, if you think about this for a quick second, what is going to be happening at 0? That means when it's not being the spring is not compressed and the spring is not compressed, the spring is not stretched. Your acceleration at that point is actually 0. Think about it this way. If I pull it all the way back, and you consider force and acceleration, or you can kind of think of them as the same thing here. If I'm pulling it all the way to the right, so that's all the way to this 0.5, right? Then there's going to be a force going to the left, which would be negative, right? And that would be the maximum amount. Now, what happens if I push that all the way in as far as I can to that negative 0.5? I'm pushing it to the left, which means now the spring is going to be pushing back on it to the right. So ironically, we're going to have so that's pushing back, that's positive. If you have a lot of force, you have a lot of acceleration. So actually it's going to start out positive and then go straight down to the origin of 0 and push back out. So here's something you need to say, and I didn't draw this exactly to scale, which is important to understand. You might have to say something along the lines of, this is going to be a straight linear line that has its maximum value at negative 0.5, goes through the origin, and then has its maximum negative value for acceleration at positive 0.5, and they are the same heights. They are the same magnitude of acceleration is something you might want to say. So you really need to, how would you describe this graph? Well, the magnitude of the acceleration is the same at both negative 0.5 and 0.5. At negative 0.5, it is positive. At positive 0.5, it is negative. It is a straight linear line going through the origin. That's how I would describe it. Sounds like a lot, but that's what they're going to be asking you to do. All right. New problem. The student hypothesized the greater fractional kinetic energy is lost in the system when the speed of first is greater. One reason this hypothesis might be correct. So you've got something that comes in, it hits something else, and then what is this one? Two-cart system during the thing depends on the speed of the first car. So the collision is not perfectly elastic, causing the new car system to lose kinetic energy. So why could it lose kinetic energy? What are some reasons? Well, in order for there to be some kinetic energy loss, some energy has to go somewhere else, right? So the student hypothesized the greater fraction of kinetic energy is lost from the system during the collision when the speed of the first car is greater. Well, let's think about a car. Let's say you're driving a car, or maybe you're even in a bicycle, and you're going slow, and you accidentally run into a brick wall. You bounce right off, right? Nothing big there. What happens if you go really fast? You're going to bounce right off? No. It's going to either do damage to your bike, to the wall, to the helmet, to you, hopefully not, but there's going to be some damage done, right? Think about a crumple zone on a car. That's damage. So realistically, what you're trying to say is, so the cart's initial speed would possibly create permanent damage. So just like your bike, if you're going real slow, it's not going to do that much. But if you're going real fast, it's going to create permanent damage. So it's like a spring doesn't actually bounce back because you just messed it up too much. Like you overstretched it is a good way to say it, because it's really hard to over compress them, but you can sort of do it. So if the car was going slower, the damage would not be permanent. Just like when you bounced your bike off the thing if you're going real slow. But at the slower speed, but at a higher speed, more damage would happen the faster you go, which would incur cause of lots of loss of energy. So if you run into that going really fast, there's going to be even less chance of you bouncing off because you're going to create permanent damage. And that permanent damage is going to sort of suck the energy out of the system. Hopefully that kind of helps with that one. All right, so how would we prove this? What are some experimental pieces you're going to need? Now, I know on yours it didn't give a table, and this is not 100% accurate because I've not seen anything to counter it. If you are given a table, I have never seen a table given that does not have enough space. Now, you may be doing it a different way, but that should be a red flag. I have seen tables given that have more than enough space, but they were also accounting for a weird way to do it. But if you run out of space, I'm not saying you're wrong for a table, which it said you have, but you didn't have on this question because of the way it was worded on the thing. But if you're given a table and they say fill it in, be cautious if you go over it. That doesn't mean you're wrong. It just means you might have more than you need. All right, so quantity to be measured to sort of prove that this works. Well, you're going to need the initial speed of the cart, the heavy cart. That's going to be H. We're going to call that VIH for heavy. I'm going to use a motion sensor. Could I use a photo gate? Singular. No. Could I use multiple photo gates? Yeah, but that gets really wonky. Final speed of the heavy car would be V final, and I'm going to use the same exact motion sensor, right? Mass of the heavy car, I'd use a scale, or if you want to be real scientific, you need a triple beam balance. Scale works fine. Final speed of the light car is V final of the light car, and we already know the initial speed of the light car, but we will need the mass of the light car, scale. Now, you will not have to draw. However, if you're given a problem like this, which I will be blown away if you're not given a design and experiment problem, I suggest drawing a picture because it's always helpful. You do not have to. This test is designed so you don't have to draw anything, but I still recommend it unless you're trying to type everything out. Now, when I drew this, there's my track. There's one motion sensor. That's motion sensor 1. There's the second motion sensor. There's my heavy cart, and there's my light cart. Now, I need an overall procedure to be used. You need to be specific. You are collecting data. You're not manipulating data, you're just collecting data. So, step 1, measure the mass of both cars and record. Boom. Step 2, set the cars and motion sensor as shown in the diagram above. Or you have to describe how you did it. That's why I like to draw pictures. Step 3, start recording motion sensor data and push the heavy cart into the light cart so they crash into each other. Being very specific here, they want specific details. Record the following data from the motion sensors. Now this is where I want the speed of the heavy cart right before the collision. I want the speed of the heavy cart right after the collision. I also want the speed of the light cart right after the collision. Well, what's the speed of the light cart before the collision, Mr. Cooper? It's 0. Now, you have collected all the data, but this is an experiment, so you need to say something about repeating the trials. Now, I've always said 3 is the minimum. That is my personal opinion. But if all you're going to say is repeat X amount of trials, because you also have to vary the force, pick a number other than 3. Don't pick a crazy number like infinity, but repeat above steps with varying force of pushing at least 10 times. So you want to repeat the above steps with varying force of pushing at least 10 times. So you want to repeat it varying force because you're supposed to try different forces. I will give you different speeds. All right. Describe how the experiment data collected could be analyzed to confirm or disconfirm the hypothesis that a greater fraction of kinetic energy is lost from the system during the collision. So how can you make sure you can prove that this is the case? All right, so each trial, calculate the initial and final kinetic energy of the heavy cart. Have to do that, okay? K initial, I want you to show equations, equals 1/2 mh v initial h squared. So that's the initial velocity of the heavy cart, okay? Kinetic final. Aha, and I need the total kinetic final, which is going to be the kinetic of the, no, this is final of the heavy, plus the initial of the heavy. Remember, I'm trying to push it into this equation up here, the K lost over K initial. So that's the K initial, right? And that's the K final. Create a graph of, this is what you're graphing, K lost over K initial, which is basically initial minus final over initial. Okay, so there's the final kinetic, there's the initial kinetic, so it's this minus this over this. But what are you going to graph it with respect to? Well, what are you really changing? Well, I'm changing the force. Yeah, you're kind of changing the force, but what are you really changing? You're really changing the initial velocity of the heavy cart. You're using more force to do that, but that's really what you're measuring, because he's saying the faster you go, the more energy is lost. Now, in my opinion, this is a weird way to phrase this, and it got me confused when I saw this answer because I wrote it differently. But I'll show you how I wrote what I. But if you think about this, what if I say I want you to grab velocity as a function of time? Well, what would you call that graph? Well, it's a V versus T graph, right? And that's really what this is. So this is what I put: a K loss over K initial versus VIH. So these two answers are the same. This is like the really velocity as a function of time, and this is kinetic energy lost. Well, the what are we talking about? The fraction. A student wonders the fraction of kinetic energy. So the fraction of kinetic energy lost, right, with respect to velocity. So whatever makes you happy. But that's how I would have done it. So we graph that. Now, but how do we know if it's true? Well, if it's true, then the graph should be positive trend. Then the hypothesis is confirmed. So if you increase the velocity, right, you should have more fractional energy lost. Well, duh. That means as you make it higher, that number lost should be greater. That number, there you go. Okay? Boom. Moving on. Consider a different scenario in which the carts stick together. So they stick together. Derive an expression for the fraction of kinetic energy lost during this collision. Now, what's going to change here? This one gets a little bit funky with the actual letters. I had to have some more room. So let's start with this. So we have our mass, heavy, times our velocity initial. Okay, yeah, it should be VHI, but whatever. Now our two masses stick together, and we have a new final velocity. Okay, that's where they stick together. Now we have to do some funky things here, because we're trying to derive an equation in terms of M1 and M2. So we've got to have this, K lost minus K initial equals something with M1 and M2. So somehow we have to get rid of these velocities here. So I'm going to say final velocity equals this, right? And all I did was divide over the M1 plus H. Okay, now kinetic initial is this, right? Mass of the heavy, don't forget that. Kinetic final is now this. It's a little bit different. The masses are added, okay? So K loss over K initial equals K initial minus K final, right? So I'm just rewriting this exactly as it says. So here is K initial, here is K final, here is K initial. That's all I've done. Now here's my problem. I've got way too much going on here, so I've got to cancel some stuff out. So first thing I'm going to do is rewrite this one more time, right? But I'm going to start distributing this stuff, okay, into this. Wait, Mr. Cooper, I don't understand what did you do here. Okay, this is VF squared, correct? Right? VF equals this, right? Squared. I got you there. So all I did was got rid of the final velocity. Because if you look at this equation, look right here. I've got initial, I've got final. Well, I got to get rid of one of them, and I'd rather only get rid of one, so the others obviously cancel out. So I'm going to get rid of this final velocity, which is why I did this up here, okay? So I got rid of the final velocity. I plugged it in where I saw VF. I plugged in this. Still had to keep the squared sign. Now, I can still do some more stuff here, right? All I did here was distribute the square sign. So this is squared, and then these individual are squared. That's all I did. Now I'm going to start getting rid of stuff. Like, for instance, the 1/2. Say goodnight, Lucy. Now I've also got some other stuff, like the initial velocities. They're all squared, so they're all gone. Ooh, I'm doing good here. Hold on, look at this bad boy, this and this, which means I can cancel out that squared, and that one. Now I'm going to rewrite it. Okay? There's my mh minus m squared h over m plus ml. I'm not done yet. I've still got this mh times 1 over mh, right? Nothing crazy there. Now, I can distribute this through as well, which means this mh is going to cancel with this one, and this mh here, which goes into this term, is going to cancel out this squared, which gives me that as my answer. 1 minus mh divided by mh plus ml. That's just some ugly algebra, but that's part of it. And this is pretty clean to show you that you understand the concepts and understand some good old algebra. All right, so that is for that problems. I'm also going to be posting the practice exam. Hope you helped. Hope that helped you. Have a great day.